Well, good morning, everybody. On our first day off here, we're gonna just keep doing our best as we all try to make way through this whole thing. Who knows how long we'll be out, but we're gonna give it our best shot, and we'll see what happens. I think we'll be okay. You guys have a great foundation moving forward from what we've learned with proportions, so everything should fall right in line with that. So we're going to start off with these notes. We'll try to get through the first couple pages today, explain the whole point of what is a one sample t confidence interval. We're going to skip the first part because that's a class activity, but we're going to jump down here, number one. I'm going to go ahead and give you a minute to read that. Pause the video if you want to, and then we'll come back and just talk about it. Okay, so the study involves 20 undergrads from University of Illinois, Urbana-Champaign, and basically what they want to figure out is how many M&Ms would people consume if you were to have a study session for everybody at the school. So what's the true number that would be eaten? Now, if we think about number of M&Ms consumed, right? The first question is that categorical or quantitative? Well, somebody might eat 10 M&Ms, somebody might eat 50 M&Ms. The question is, can I average those together? And definitely, I can average those together. We want to figure out the mean anyways. So this is going to make us come back to quantitative data. And this should be our huge focus, right? Our entire last unit was dealing with categorical data. Categorical data, remember we worked with proportions. We make bar graphs, right? And we worked with all that stuff. That was everything that we did before. But now we're in quantitative data. Quantitative data means we're going to be talking about means. So means are going to be a key phrase that we're looking for. We have a bunch of different graphs. We have dot plots, we have histograms, we have stem and leaf plots. So we got all those different things that we could make there. Obviously dot plots here as well. So we're going to be focusing on these. And if we take a look, we see we had 20 people at our study session. On average, they ate 50.15 M&Ms. So which is actually kind of interesting. There's about 54 if you were to buy a bag. So it's funny that it's around that same number. Standard deviation. Remember, that's the typical distance a value falls from the mean. So if our mean is somewhere in here, the typical distance that a student is away from that is about 30 M&Ms. So pretty large standard deviation. But we're talking about college kids, right? You know, maybe these kids hadn't eaten in a while. Maybe it's the end of the semester. So they were really hungry when they came in. And some people, you know, maybe just had lunch and already had dessert. You know, you get all the desserts you want in college. So some people didn't eat very many. So anyways, we can see all this stuff. Don't forget, here's our 5-number summary, right? This is always important. Our min, Q1, median, Q3, and the max. So always things that we want to be looking at. You know, questions I'd ask yourself. Do you know how to find an outlier based off of this data? So don't forget you got your formulas Q3 plus 1.5 times the IQR, or Q1 minus 1.5 times the IQR. Let's always just make sure that we're asking ourselves these bigger questions, just to make sure that we remember all that stuff. All right, first thing it asks us, describe the distribution. Okay, and I typed this out for us because we're in a video trying to save some time. But remember what this is asking you to talk about is this asking you to talk about the shape, outliers, center, and variability. And don't forget, you always have to come back and talk about this thing in context, context, context. So I said the distribution of the number of M&M candies consumed has 2 distinct clusters. I kind of said there's a group down here and a group up there. One that's skewed to the left and one that's roughly symmetric and centered around 100. The mean number of M&Ms consumed is 50.15 in a study session, and the typical student is about 30 M&Ms away from the mean during the review session, which is just our definition of standard deviation. So here's where we get to. This is where it's getting really important. So are the numbers 50.15 and 30.31 parameters, or are they statistics? Now remember, a parameter is a value that comes from the population. So was this based off of every student at the University of Urbana? No, it wasn't. These would be statistics. So remember, we're going to be working with statistics, and our goal is to try to figure out the parameters. So we always have to know our symbols. So what symbol would represent a sample mean? That's always our X bar. And we haven't seen that in a little while. What number represents sample standard deviation? That number is S, 30.31. So these are very much statistics because these are all derived from samples. Now, just so you guys are aware, as you're working through the video, feel free to pause it, take your time, rewind it. You know, that's a great part about a video. I'm going to hustle through it just because I think it's going to be long enough anyways. But pause it as you need it to go back and make sure you understand this stuff. So here's the question. If these are statistics, what is the parameter of interest? What did we want information on? Well, we wanted information on mu, right? The true mean number of M&Ms consumed by all students at University of Illinois Urbana-Champaign. Do I know mu? And the answer is no, right? We don't know mu because we know the sample mean. The only way to know mu would be to give this out to every single student there. And that would be pretty costly if you think about that. I don't know how big the school is, but we could see that that's there. So here's the deal. Do we know the value of the parameter? No. Why not? Because we always know statistics, the x bar and the s, but we don't know parameters. So here's the question. Is mu close to 50.15 or far away from it? And this is all coming back to our sampling distribution of the sample mean. Now remember, we have 3 rules for the sampling distribution of the sample mean. Number 1, the center. The mean of the x bars is always equal to mu as long as we take a random sample or a random assignment of the treatments. Okay, so yeah, in the long run, these x bars would be centered around mu. So that's good news. Now, we don't know if this one is or isn't, but in the long run, it would be. Number 2, the variability. And we like this a lot because remember, when we take groups of things, the standard deviation of the x bars is your population standard deviation divided by the square root of the sample size. Remember, groups pull closer towards the mean. Now remember, this has to give us our 10% rule as well. And the last thing, what about the shape of these x bars? Now remember, we had 2 rules for the shape. If you go back, number 1, it'd be normal if the population was normal. Or number 2, and this one was a beautiful thing, if our sample size was at least 30, then it'd be approximately normal by our good friend central limit theorem. Okay, so I don't have a sample size of 30. I don't know that the population is necessarily normal. So, we're a little bit stuck here on that. We might look at the data and see if that looks normal. But in this case, this is just in general what it would be like. So let's just draw a quick picture because it always helps us out. We don't know mu, but if we did, right, we know that the mean of the x bars would be centered around mu. We know that. We know that the standard deviation of the x bars is sigma over the square root of n, so it'd be kind of close to it, right? And then the shape is the normality thing that we've already talked about. Now remember, these are how the x bars deviate away from the parameters. But we don't know the parameters. That's the problem, right? We don't know the parameters. But we know it should be close to it, or roughly close. We would know at least 95% would be roughly within 2 standard deviations. So that's pretty good to know. So let's keep going with this thing then. And you might see the parallels to proportions that we've done. So here's the thing. If we don't know sigma for this M&M study, well, do you know sigma? And the answer is no. And then the question is, what is sigma? So sigma is it represents the population standard deviation. In this case, it would be the typical number of M&Ms consumed away from the population mean of all students at the University of Illinois, Urbana-Champaign. So I don't know sigma. So if we did, that would be a beautiful thing, but I would have had to give this out to every single student. How many students did I give it out to? Only 20. So my standard deviation of those 20 is probably different than the standard deviation of whatever the 20,000 people would be like. So let's just pretend that we knew sigma. If we did, we can go ahead and make our confidence interval just like this. We take the sample mean, which remember is our point estimate. In the last chapter, it was p hat, right? Because there's a sample proportion to estimated population proportion. Now it's an x bar to estimate mu. So that's our point estimate. This is our best guess for mu. You'll notice now that we have z star, right? The same critical value. Remember, that's our critical value. And sigma over the square root of n, right? Which this whole piece is my standard deviation. But remember, this whole piece right in there is just my margin of error. And that gives me an estimate of how far away the sample should be away from the population mean. So here's the thing, though. This would be beautiful, but what don't we know in this formula? We don't know sigma. If we knew sigma, this thing is beautiful. It would work. But we don't know sigma. So what's our best guess that we can replace it with? So again, you got to pause the video and make sure you ask yourself this question. I don't know sigma. Sigma is the population standard deviation. So what is my best guess? What's my only guess for the population standard deviation? And after you ponder on that, you'd come back and you'd say, well, the only thing that could estimate the population standard deviation would be the sample standard deviation. So we're going to replace sigma with s. All right, so we're going to go ahead and replace the population standard deviation with the sample standard deviation. Why? Well, that's my only guess of the variability. This is the only thing I know about how far students vary away from the mean. I want to know sigma, but I would need everybody, so I've got to replace it with my sample. Now, what do I mean by that again? Coming back here, the standard deviation of these 20 people is my best guess for the standard deviation of the 20,000 students at University of Urbana, Illinois, Champaign, whatever it might be. So this is my best guess for that. It's my only guess for that. Okay, so we understand that part. So let's keep going with that. So what again is S? So S would be the typical number of M&Ms consumed away from the sample mean for our sample of 20 students. And the thing is this is probably different than sigma because I only have 20 students. Their standard deviation might be larger or smaller as opposed to looking at all 20,000 students. Okay. But if I only know sigma, or if I only know S and I replace sigma with S in that formula, we now replace sigma with S, and we now call this our standard error of the sample mean. So instead of being the standard deviation of the x bars, that would be sigma over the square root of n. We now replace sigma with S, and we start to call it standard error of x bars. And you probably remember this. We did the same thing when we replaced pi with p hat in the formula. And again, this is my best guess for that. Okay? So let's calculate the standard error. So the standard error of the x bars, how far, and we'll go ahead and write that out. So that would be S over the square root of n. So remember, S is my sample standard deviation. Okay, I believe it was, I don't want to mess it up on the video. So it is 30.31. So we're going to do 30.31 divided by the square root of 20. Alright, so 30.31 divided by the square root of 20. I have to calculate that out. Let's see what we get. So 30.31 divided by the square root of 20 is 6.78. Okay, so it's 6.78. Alright, now we got to ask ourselves, what the heck does this number mean? Standard error of the x bars is how far away the sample mean is away from the population mean. So that's our interpretation of this. So the typical sample mean of M&Ms consumed will be 6.78 M&Ms away from the population mean. Mu, right? Okay, so think about that. If the typical sample mean is 6.78 M&Ms away from the population mean, and we know that this might be roughly normal maybe, couldn't we use this idea of going out 2 of these now? Let's reach out 2 of these, and we might be about 95% confident. Okay, so let's see. So we would do 50.15 plus or minus 2 times 6.78. Now, why am I using 2? Because that's roughly 95%. Alright, so we have to calculate this back out, and let's see what we get there. Okay, so with the power of the internet, I've got 36.6 to 63.7. And what do I think I have captured in there, right? So again, if we kind of come back to that same definition before, I'm not trying to capture pi anymore, right? So we'd come back and say, hey, you know, we're roughly, and I'm just going to say we're 95% confident at this point, that the interval 36.6 to 63.7 captures the true mean number of M&Ms consumed by all UC students at a study session. And there we go. And this is informal. This is actually not right, but that's okay. Alright, so that's our best guess. So look, we think that mu is somewhere in that interval. Now, do we know if mu is in there? And the answer is no. We don't really know as of right now. But that's our first step that we have. Okay, so let's move on to this thing. Right, it makes sense. We went out 2 standard errors just like we did with p-hats. So here's the question. How well does our confidence interval perform when we replace sigma with S? Now, this is going to be a really important part of this activity. And I want you to maybe take some time to go around and mess with this in Rossman Chance. I'm going to go ahead and do it with you guys. But I want you to take a chance and go mess around with that if you get a chance to do it. So let's see what we have here. There's 3 main questions we're going to be asking ourselves. Okay, number 1, if we knew the population standard deviation, does the Z formula for a confidence interval work? Okay, that's the first one that we wrote down. You probably assume that it would. It was in the notes. Number 2, if we didn't know the population standard deviation, and instead we replace it with the standard deviation from the sample, so we replace sigma with S, does the Z formula for a confidence interval still work? That's the question, right? And number 3, if it doesn't work, what do we need to adjust in the formula to create an approximately correct confidence interval? So these are going to be the 3 questions that we go ahead and answer. Now, I've already set up the activity in my website here, so I'm going to go ahead and do that and try to work our way through it. If you are needing to know where to go, if you go to that Rossmann Chance applets and you go to simulating confidence intervals for a population parameter, and you just change this to means, it'll let you go through the whole activity as well. And all the directions there, strongly encourage you to mess around with it. So here we go. We're going to start off with this thing. So we're setting mu as 50. Now again, this is kind of weird. We wouldn't ever know mu, right? There's no point in doing confidence interval if we know mu. We're setting sigma at 30. So notice I know what sigma is. We're setting n as 20, so I'm taking 20 people from the population. And we're telling you that the population is normal as well, so make sure you understand that. That's important. Okay, so I'm going to go ahead and generate an interval. And what you'll notice is this one is green, right? Why is it green? Well, what was the mean of the population? 50. Do you notice how 50 is captured inside of my interval? Look, it goes from 29.9 to 56.3. Everything looks beautiful here. A couple of things that I want to make note of. Right here is my sample number 1. So look, the mean, this is the mean of the sample. It's 43. That's the center right there, right? 43 is the middle. Number 2, the standard deviation of my sample is 24. What was the standard deviation of the population? It was 30. So the first thing that we might notice is, do these match up exactly? And they don't. Okay. But that's okay, because right now we're knowing sigma. So if you remember from our formula, right, the formula that we're using here is that we are using this formula. We're doing x bar. Okay, so let me just come back and write this. My pen's trying to click in. We're doing x bar plus or minus z star sigma over the square root of n. So each time I'll get an x bar, and I will add to that 1.96 because I'm doing 95% confidence. Okay, sigma, which we set as 30, divided by the square root of 20. So what might you notice? Every single one, what's the only thing that's going to change? Is the x bar. Okay, so let's see how that goes ahead and affects our intervals. Okay, so here we go. I'm going to jump up to 200 of these bad boys, and I'm going to sort them just like we have done before. Which ones do we notice are capturing it? Which ones are we notice are missing it? Hey, look, all the ones down on the low end that have x bars that are more than 2 standard deviations away, or x bars that are more than 2 standard deviations above, they are the ones that are missing it. But what do you notice about the widths of all of the intervals? They're all the exact same. So all of the widths are the same. Well, why is that true? Well, because in every single one, we add and subtracted the same value, right? We had the same margin of error for every single one of those. Okay, so let's again just go ahead and take a look. Let me generate 1,000 of these. All right, or let me keep going just to make it so it's good. All right, here we go. I generated 3,200. What is my approximate capture rate? My capture rate's 95%. What does that tie in with? My confidence level. All of this stuff is the exact same that we've seen before. All right, so let's answer a couple of these questions. So we can see that 95% of all of them, right, all of the possible intervals succeed in capturing mu, the population mean. Isn't that good news? Yay, that's great news, right? Because that means my method works. That means my method works. So our first question was, does knowing sigma and using x bar plus my z star, does that work? And the answer is yes, it does. So we'll put a big smiley face for this one. This works. But here's the problem. What didn't we know in the original problem? We didn't know sigma. You need mu to know sigma. So, but usually we don't know sigma. Oh no. So usually we don't know sigma. So we're going to go ahead and replace sigma with an S. And we're now going to go see how that thing works. Now notice, all of these are the exact same width. I want to just come back to the notes here just to make sure I'm answering each of these questions as we're working through them. So which one's red? Okay, we talked about that. Okay, so I'm now going to replace sigma with an S. So now I'm going to use the sample standard deviation to generate my confidence interval. Okay, so let's go ahead and take a look. So I'm going to replace Z with S. I'm just going to start off by generating one interval. Okay, I'm going to generate a different one because I don't like that one. I'm going to keep, oh darn it, I missed the one I wanted. Okay, let's go with this one. Okay, so now my formula does this. In this scenario, I'm going to take my x bar, which is 55.8. I'm going to add and subtract 1.96 times s. I'm not going to use sigma anymore. I'm now going to use s, and s is the sample standard deviation. Notice this time it's only 23. Okay? Before it's supposed to be 30, so you might notice that that's smaller. But let's just come back here. So now I'm going to do x bar plus or minus z star s over the square root of n. So in this interval, it was what? 55.8 plus or minus 1.96 times s, which was 23 over the square root of 20. Now, what was this number before in the numerator? This was 30. Notice it's smaller. Okay? What would happen if I generated a different interval? Right? So let me generate another one. Notice s this time is 21. So, but x bar is close, it's 52. But now I'm only adding 21. So you might notice that in each case, now this time I'd go out 34, right? So each time the margin of error is going to be changing. So here's the question. What happens if I do a bunch of these things, right? So first, let's go ahead and sort this thing. And you might notice a couple of weird things happen. Okay, wait a second. Where were all of the red ones before? All of the red ones before were at the ends, weren't they? Are all of the red ones at the ends this time? No, there's all these ones mixed in here. Uh-oh. So that seems to throw things off a little bit, doesn't it? It used to be nice and orderly. Like, look at this huge thing. Look at this. Do you see this huge interval? Look at this standard deviation of the sample. It's 48. So think about how far you're reaching out from the middle. You're reaching out way farther than you should. Now, that's a good thing because you captured it. But, like, look at this one. This one missed it. It should have caught it. Look, all the ones around it caught it. So why did this interval miss it? Because s is only 20. What's it supposed to be? 30. So I'm not quite reaching out far enough. Do you guys notice that? And look at my capture rate. Let me get a bunch of these things. My capture rate's 93%. What is it supposed to be? It's supposed to be 95%. And I could keep going here when taking a bunch of these, but you'll notice my capture rate's not what it says. It is way lower than 95%. And that's not good, because I'm saying it's 95. Okay, let's see if this gets better or worse. Let's take a sample of size 10. So notice, there's only going to be 10 values over here now. Okay, so there's only going to be 10 values. So do you see there's only 10 blocks? Before there was 20. Now, like, look at this standard deviation. It's 38. That's a good one. So let's see. Let's generate a bunch of these, and let's sort them. Holy cow. Did this get better or get worse? This got way worse. Look at this. Look at this red guy. Look at this standard deviation. It's only 15. What is it supposed to be? This is S. Sigma is 30, so this is half of what it should be, right? So let's just come back here and just jot that one down. It doesn't even matter what X bar was. I'm going out 1.96, right? I'm going out 1.96. 15 over the square root of 10. I should be going out 30. And so what are you noticing about the widths? All of these widths now are so different, right? If I get back to the right page, look, all of these widths are so different. And if I take another sample, again, you see it. Look, skinny ones, wide ones. Why? S is just changing this. Wow, look at this one, so far off. Look, the sample mean was 77, but and the standard deviation 12. So this one did an awful job, right? But this thing's like huge. Why? Because you can have so much variability. So here was question number 2 that we had. Does replacing sigma with S, does it work, right? What's my capture rate? Look, it's down to 88%. Let me keep going. I'll get more for you. Okay, wow, I'm at 90%, 91%. What's it supposed to be? It's supposed to be 95. So in question number 2, does replacing the standard deviation of the sample, replacing sigma with S, does it work? And the answer is no. The capture rate is too low. Uh-oh. So that means this formula, x bar plus or minus z star, s over the square root of n, doesn't work. Well, what if I go back to a bigger sample size? Let's take like 30. Let's do 30. So now I'm going to take 30 values. Now does it seem to be working a little bit better? Yeah, it seems to be working a little bit better. And the question might be why. Well, think about it. The more values that I take, the better job S will do at figuring out sigma. But the less things that I have, the worse that it will do. So it seems to work fine for 30. Doesn't seem to work very fine for 10. And that's going to be a big problem here. All right, and so we're going to start to dive into this. So what happens if what do I need to do? Well, this whole thing brings us to a very new idea that we need to come up with some sort of new distribution. All right, we need to come up with some sort of new distribution. And this is going to be what's called the t distribution. So we're now going to replace z with this new distribution called t. So we're going to change it to this. Now why? Well, what was happening when I replaced sigma with s? The intervals were too small. Why were they too narrow? Because s was doing a bad job at estimating sigma. So if the interval was too narrow, what do I need to do to my interval to make it work properly? And if you said make it wider, you would be exactly correct. So what the t distribution is going to do, it's not going to use 1.96 here anymore. It's going to replace it with some new value. So let's go ahead and see that actually happen. So I'm going to come down here, and I'm going to start off with sample sizes of 10. Okay, I want everybody to watch this. I'm going to change it to t distribution. Watch closely. What happens? 1, 2, 3. Did you notice the intervals? Okay, right, I'll do it again. Z with S, switch to t. Do you notice how the intervals get wider? And as they get wider, look what happens to my capture rate. Look at it. It's 95%. What should it be? Holy cow, look at this one. That one's crazy. Doesn't matter how much wider you get for that one, right? The standard deviation is only 7. But like, look, these other ones are all compensated because they're reaching out further. Well, let's see. Does it work if I go to 20 values? Let's see. So let me start off with Z with S. Okay, I'm going to change it to T. What do you notice? They get wider. Now, not as wide as before, right? But they got a little bit wider. But is the capture rate approximately correct? And the answer is, yeah. Well, what if I have all the way up to 30? Let's take 30 values from the population. All right, so here's 30. Again, I'm going to change it to T. Very slightly wider, but it is wider. All right, so here's the deal. We now know that if we replace sigma with S, we can't use the normal distribution. We now have to use this new distribution called the t distribution. All right. Now, the t distribution, instead of just one thing, is going to be a family of curves. And let's go through and just read this part together and just see what this looks like. So the problem with replacing sigma with S is that fewer than 95% of the intervals succeeded in capturing mu when the sample size was small. Two things happen. The sample mean will tend to be further away from the population mean than expected, and the sample standard deviation will tend to be less than the population standard deviation. S was a bad job at estimating sigma. To compensate for this, we must make the intervals longer so that they're more successful in capturing mu. And to do this, you have to use a different multiplier than z. So z is out. No longer normal. We're now in this distribution called the t distribution. We've already talked about the letter t here. So here's my new formula for a confidence interval for a population mean. X bar is still going to be my point estimate. Okay, so X bar is still my point estimate. Now, but instead of this part, my margin of error being Z, sigma over the square root of n, my margin of error is now T, S over the square root of n. Okay. Now you'll notice here that it also says degrees of freedom are the sample size minus 1. I'll show you that here in a second, because the t distribution is no longer just one curve. It's now what we call a family of curves. So here's a normal distribution. Now what has to happen? The t distribution has to spread things out more. It has to go out wider than what you'd expect. So this says the green one is a t distribution with degrees of freedom of 1. That means my sample size is actually 2. And what do you notice about it? Oh, it's lower in the middle. It's still symmetric, mound shaped, but it's lower in the middle. And it has more area outside here. We say that it has fatter tails because you'd expect things to be further away. Now, remember what happened? When my sample size got bigger, I had to compensate less because S was doing a better job at estimating sigma. So here I'm making the degrees of freedom get bigger, and what do you notice about it? It's getting closer and closer to that to that normal distribution. So as my degrees of freedom get bigger, the t starts to look more and more like a normal distribution, and really kind of 30 or 40. A lot of textbooks use 40, where it's basically indistinguishable. We're not going to do that in AP Stat, But the big idea that we need to know is that t-distribution, when the sample size is small, is going to be symmetric, mound-shaped, but it's going to have more area in the tails because we're going to expect things further away. Okay, so in order to use this, there's going to be 3 conditions that have to be met. And this is going to be slightly different, but we're going to work through these in the notes as well. Number 1, the data must come from a random sample or a random assignment. Number 2, you have to have your 10% rule. Okay, so that's going to still hold there. Now, number 3 is going to be a new one. This is going to be our normal large sample size. So here's the deal. If the population has a normal distribution or the sample size is bigger than 30, you're good to use the t-distribution. But that's not going to happen in a lot of cases. So if the population distribution has an unknown shape and n is less than 30, then we have to use a graph of the sample data to assess the normality of the population. And basically what has to happen, in order to use t, we need the population to be approximately normal. And if the data doesn't show any skewness or outliers, then we're going to be fine to use it. So I have 3 examples here of just looking at the shape of the sample. And then we'll dive into doing some of these. So to estimate the GPA, you randomly select 50 students, and here's a histogram of the it's supposed to say GPA instead of GPSs. So here's the question. Is the normality / large sample size condition met? And this one, it is totally yes, right? Why? What do we notice? 50 is greater than or equal to 30, so we have so we can use a t-distribution. Really, that central limit theorem is kicking in. X bars are approximately normal, so we're good to go. All right, how about letter B? How much force does it take to pull wood apart? So the stem plot shows the force in pounds required to pull a piece of Douglas fir. Now notice my sample size is only 20. That doesn't count as my large sample size condition, does it? So now we look at the data. Is the data symmetric with no outliers or strong skewness? And the answer is no. Can't use t. The data n is less than 30, and the data is strongly skewed with outliers. So our capture rate wouldn't be correct. It is skewed with outliers. Left with outliers. Now if it was symmetric, we'd be good to go. Okay, so let's take a look at C. So is it just all about the sample size? Suppose you want to estimate the mean SAT for students of 20. Now look at it. N is 20, so it's small. But this data looks roughly symmetric. There's no outliers. It's not strongly skewed. So yes, we can use T. And this is really about the extent of it, guys. So yes, we can use t-distribution. There's no skewness or outliers. All right, and there we go. All right, so we've talked about our t-distribution. And now we need to show you guys how to get those t values. So how do we figure out these new values for, instead of z, our critical values, how do we find these t critical values? All right, we have a new formula sheet that we're going to be using. And I have this at school if you need to pick it up, but it's called a t-distribution table. Okay, so here's the one that we have. I've posted this on the classroom as well. So it basically works like this. At the bottom of the t-distribution, make sure you're on the t. This is way easier, honestly. They give you the confidence level, and on the left-hand side, they give you the degrees of freedom. So remember, degrees of freedom are sample size minus 1. So let's take a look. How far out would I have to reach if I want to do a 95% confidence interval with a sample size of 12? Okay, so first question, my degrees of freedom would be 12 minus 1, which would be 11. Okay, and my confidence level is 0.95. Okay, so here's what I do. I go to my formula sheet, I find 95% confidence, and I scroll up until I find 11 degrees of freedom, and my critical value would be 2.201. It's this value right here. So 2.201, 11 degrees of freedom, 95% confidence, 2.201. So T star would be 2.201. Hey, what do you notice about that compared to Z? It's bigger. Z would be 1.96. And that's a big thing. The T star is always bigger. Bigger than Z star. Why? Because we're compensating for replacing that population standard deviation with a sample standard deviation. Okay? Next one, a 90% confidence interval from a random sample of 48 observations. Okay, so my degrees of freedom would be 47. And we go back to our table. So we go 47 and 90. So 91st, 47, uh-oh, it's not on here. 47, 40, and 50. Okay, so which one do we go with? So you could either go with 1.676 or 1.684. Now remember, what's our whole goal? To go out wider. So which one would make you go out wider? 40. So even if it's not on the table, you always round lower. So even if it was 49, you'd use 1.684. So my t star would be 1.684. All right, and now that's our best guess for it, right? So we would always round down on that. And you guys will be able to use calculators and all that stuff to help you out when we get to these. All right, we can use the Inspire to help us out with this. I'll just show you this real fast. Here's how this works in Inspire. You use your inverse t feature. So you do everything just like before. You remember inverse norm. So you go menu 5, 5, or 6, 5, it doesn't matter. And you go to inverse t. So the area, remember, if it was a 90, let's do a 90%, let's do a 95% confidence interval. Let's do the first one. Remember, you have to do 0.975. And your degrees of freedom would be 11 for the first one, 2.201, and that's basically what we had here, 2.201. Okay, so that's how you could do that. Just remember you had to cut off that difference on the ends. All right, we're doing great. So let's get ready to put this whole thing together. So now we're going to do one all the way through. All right, I'll let you go ahead and read the question. We'll come back in a second, take a look at it. Okay, so the Pew Research study found that in a random sample of 1,520 Americans, so that's N, the sample mean was 12 books read, so X bar is 12. And the standard deviation of the sample was 18, so S equals 18. So here's the first question. Categorical or quantitative data. Number of books read, quantitative. So we're talking about means, right? Question 2, do we know sigma? The answer is no. And if as soon as we say we don't know sigma, that tells us that we're using the t-distribution. Okay, so let's go ahead and dive into this thing. They want us to make a 95% confidence interval for all the books read in the previous 12 months. So we're going to go through panic. Now, my parameter of interest is mu. It is the true mean number of books. Sorry for the bad writing. Read by all American adults. That's my sample, so that's my population. By all American adults. All by all American, oh well, it's okay. Adults in the last year. Okay, good to go. So we're going to go to our conditions. Number 1, we were told there's a random sample. Good to go. Number 2, we know that there's more than 10 times 1520, 15,200 Americans. So we're good there. Okay, number 3, we need our normality large sample size condition. Well, we got it. 1520 is bigger than 30, so we can use the t-distribution. Excellent. This is pretty easy, huh? All right. So number n. So now this is going to be called a one sample t confidence interval. And as soon as we put t in there, we're going to throw in our degrees of freedom. So my degrees of freedom would be 1520 minus 1, which is 1519. Okay? All right. So let's go ahead and grab our interval now. The formula looks like this. X bar plus or minus t star s over the square root of n. I want to use sigma, but I don't have it. Place it with s, and that's where t comes in. Okay, so this would look like this. So it would be 12 plus or minus. Okay, now we got to go grab t star. So my critical value, how far should I reach out? Now, if it was x, if it was z, it would be 1.96, but it's not. It's going to be t, so it's going to be a little bit wider. So if I go to my formula sheet, 95%, the closest that I can get is 1,000. Now notice infinity, actually this is actually your z star down here. 1.96 is z. So you'll notice t gets closer to z. So I'm going to use 1,000. That's my best guess. So I'm going to go out 1.962. And again, I'm not having to compensate very much here, right? So it should be 1.96. 1.962 is really not much further, right? Well, why? Because S is probably doing a pretty good job of figuring out sigma at this point. 18 divided by the square root of 1520. Okay, we got to go calculate that out. So I came up with the interval 11.09 to 12.9. And now we want to go ahead and conclude with that. My pen died, so it's okay. So we're just going to say we're 95% confident. The interval 11.09 to 12.9 captures the true mean number of books read by all American adults in the last year. And there we go. Now, final question says part B. Pew reported that average was 14. Does this interval provide convincing evidence that it's different than 14? And the answer would be, yeah. What value is not in that interval? 14, right? So I'm just going to come back here and say B. 14 is not in the interval of plausible values of mu. So yes, we think it's different. And there we go. And I know you can't really see that very well, but that's okay. All right, so there's that first one that we took a look at. All right, why don't you take a look at the next one? We'll come back and look at that together. Okay, so we're talking about these miniature horse, and we can see that mu is going to be the true mean shoulder height of this species of miniature horse. We're talking quantitative data. Mu, do we know sigma? The answer is no, so we don't know sigma. We replace with S, which is telling us we're going to be using the t distribution. Again, these are the same things we go through each time. All right, so here's my P, my conditions. Assume it's a random sample of horses, more than 10 times 70 possible horses. Now, the last thing we have to check is our normality condition. Now, sample size is 7. Is 7 bigger than 30? No. So I have to go look at the data. Okay, so I've got it in here. I'm just going to make a graph of these ponies. So I'm going to add a page, and I'm going to add in my number 5, and I am going to just take a look at a dot plot. Does this look symmetric with no outliers? Sure, it looks decent. I can also add in a normal probability plot, which would be perfect to do in here, right? So remember, if I look at normal probability plot, does the data fall on the line? Yes. So therefore, we can say that the population is approximately normal. So I'm going to go ahead and just copy this down on my paper, and I'm just going to kind of just do the 7 dots that I have, and I'm going to put the heights down here, right? So we can see that. So the normal probability plot shows a linear pattern. So what that lets us assume is the population is approximately normal. Because if this sample is approximately normal, then if the sample is approximately normal, we can assume that it came from approximately normal population. So it shows a linear pattern, can assume the population of heights is approximately normal. All right, great. So I have my normality condition. Now, what are you going to do at home? You might have to use another website, and I'll show you that here in a second. Okay. So now we're going to name the interval. So this is a 1 sample t interval. Anytime we write t, we have to grab our degrees of freedom. So it'd be 7 minus 1, which would be 6 in this case. Okay, my formula looks like this. I'm kind of hustling along here. I'm running low on battery. T star s over the square root of n. Okay, I don't have x bar, nor do I have s. So I need to go get that from my calculator. All right, and I'll just run my 1var stats. So menu, stat calculations, 1var stats. And I know some of you guys might not have calculators at home. Again, I'm going to show you a way around this pony. Okay, x bar is 46.1, s is 1.18. All right, so 46.1 and 1.18. All right, I need to grab my t star. So 6 degrees of freedom, 98% confidence. So I'm right there, 6 degrees of freedom. Keep scrolling up, and it is 3.143. So you can see that number right up there, 3.143. So 3.143. And now notice that's reaching out pretty far, right? 1.18 over the square root of 7. All right, now one thing that's really nice to do is I can also just use my calculator to do the whole interval. So instead of doing this, watch, I'm just going to do everything right at once. Menu, stat, confidence intervals, t interval right there. Now, do you have data or stats? Stats is if I just had x bars and s's. I have the data, so I click data. It's pony. I want 98. And this is going to give me everything except for t star. So notice there's my lower, upper, x bar, degrees of freedom. S gives me everything that I need. N, all that stuff. I do have to go write the t star down though. So it's 44.7 to 47.5. So 44.7 to 47.5. So there's my interval, and I come back in my conclusion and context. So now we just simply have to say we're 98% confident this time. So we're 98% confident. The interval 44.7 to 47.5 captures the true mean shoulder height of this species of mini horse. And there we go. All right. Um, the last thing that you might need to come back to is just come back and say, hey, what does it mean to be 98% confident? 98% of all the possible intervals will succeed in capturing the true mean shoulder height. So that's a question we've seen. All right. So let's say you're home, you don't have a calculator, all right, and you're just figuring this out. So if you go to Rossman Chance, if you go to theory-based inference right down here, and you click one mean, so in the scenario, and you click paste the data, you can just type in the data for all of your horses. So I pasted it in without a header. I click use data, it gives me n, x bar, s, gives me everything. The graph, so I can jot that down and say, hey, there's no outliers, so I can use t. And then if I just select over here confidence interval 98 and calculate, it gives me the confidence interval as well. So this thing's beautiful. You could change it for a 95 if you wanted to, or whatever it was doing. Again, it doesn't give you the t-star, but it gives you all the work, the graph, everything that you need. If you were home, if you just add the x bar and s, you can just paste that in as well. Obviously, it wouldn't give you the graph then. Okay. So there's all of that. So hopefully this is all looking good so far. There's one last thing that we have to do. Is our last thing would be the margin of error question. So why don't you take a minute, go ahead and read through the. So once we understand, again, the idea of a confidence interval, then we're going to come back to the question of, hey, what sample size might I need before I ever get started? And so we're doing 95% confidence. They want their estimate within 1 milligram. So that's my margin of error. We want it to be within 1 milligram. We're trying to figure out mu, so my confidence level is 95%. And they tell us the standard deviation is 5. So typically we would use this, right? We don't know the population standard deviation, so we'd use this. But this gets to be too much of a guessing game, because t depends on your degrees of freedom, which is based off of the sample size. I don't know the sample size, so it just starts to get confusing. So we don't really use this formula for margin of error. Just think for margin of error, you're always just going to be using this part, right? We want the margin of error to be at most. We're going to do z star, and whether it's s or sigma over the square root of n, it doesn't really matter. This is just going to be our best guess. So I want it within 1. We have a z star, now it's 95% confidence, so 1.96. Again, one of the beautiful things about this new formula sheet is if I come down here and see 95% confidence, the very last row is z star. So you guys really don't have to remember any of those anymore. So 1.96, s is going to be 5, divided by the square root of n, and that's what we want to go ahead and solve for. So walking through how to solve this, the first thing you would do is divide by 1.96. So I got to use my calculator here. So 1 divided by 1.96. Oops, don't want that. Alright, so 1 divided by 1.96. Okay, is 0.51. And again, I'm just going to put that on my paper. But again, remember we don't round. Okay, so now I multiply both sides by the square root of n. So I get 0.51 square roots of n is at least 5. At this point, I divide both sides by 0.51. So I have the square root of n is at least, so 5 divided by that number before, and it's 9.8. And then obviously I have to take both sides and now square it. So we square both sides, and so n must be at least, so we square that, and it's 96.04, and we have to make sure that we take that value and increase it. So n must be at least 97 monkeys. And there we go. All right. So guys, that's the whole unit, or the whole part with T confidence intervals. Feel free to watch the videos as many times as you want. Mess around with the applets. I've posted the homework. The homework has all the videos that are attached with it. So please go check those out. They'll be a big help, I promise. I'm going to try to hold office hours. So I'll send an email out about a time that I'm going to be available to go over some of the homework if you have questions. And just you can respond back. I might just set a couple times, maybe on like Tuesday and Wednesday morning. You can just log in with a Zoom account, and we'll just go from there. So, listen, I hope you guys are all staying safe. Hope you guys are all staying healthy. Miss you guys. Thinking about you. You know, we're going to get through this together. We're going to do a great job. So, be well, everybody. We'll talk to you soon. Bye.